Welcome. Today, we are going to tackle a challenging problem from the 2023 Cambridge University Undergraduate Admission Assessment. By the end of this video, you will be able to solve second-order linear, non-homogeneous recurrence relations by breaking them down into complementary and particular parts. Here is our equation. Notice it is non-homogeneous because the right-hand side is n squared, rather than 0. To solve this, we use the principle of superposition. The general solution, u sub n, is the sum of two parts, the complementary solution, which we will call u sub n superscript c, and the particular solution, u sub n superscript p. Let's start by finding the complementary solution. To find the complementary solution, we look at the homogeneous version of the equation, where we set the right-hand side to 0. We assume a solution of the form u sub n equals lambda to the power of n. Substituting this into our equation gives us the characteristic equation. By dividing through by lambda to the power of n, assuming lambda is not 0, we get a simple quadratic equation. This is a standard quadratic that factors easily. We are looking for two numbers that multiply to 6 and add to -5. So, our characteristic roots are lambda equals 2 and lambda equals 3. The complementary solution is a linear combination of these two terms, where a and b are constants determined by initial conditions. Since we weren't given initial conditions, we keep them as general constants. We have now met our second objective. Next, we need to find the particular solution, which accounts for the non-homogeneous term, n squared. The method of undetermined coefficients suggests that if the right-hand side is a polynomial of degree 2, we should guess a particular solution that is also a polynomial of degree 2. We need to find the values of the constants a, b, and c that satisfy the original recurrence relation. Let's substitute this guess back into the original equation. U sub n plus 2 minus 5u sub n plus 1 plus 6u sub n equals n squared. Substituting our guess into the equation, we replace u sub n plus 2 with a times n plus 2 squared, and so on. Now we expand each term carefully. The first part becomes a times n squared plus 4n plus 4 plus b times n plus 2 plus c. Then we have minus 5a times n squared plus 2n plus 1 minus 5b times n plus 1 minus 5c. And finally, plus 6an squared plus 6bn plus 6c equals n squared. Take a moment to look at the grouping. We will group the terms by the power of n, the n squared terms, the n terms, and the constant terms. For n squared, we have a minus 5a and 6a. For n, we have 4ab minus 10a minus 5b and 6b. And for the constants, we have 4a, 2b, c minus 5a, minus 5b, minus 5c, and 6c. Simplifying the coefficients, we get 2a times n squared, plus the quantity minus 6a plus 2b times n, plus the quantity minus a minus 3b plus 2c equals 1n squared plus 0n plus 0. By comparing the coefficients of n squared n and the constant on both sides, we can solve for our unknowns. Now, let's solve the system of equations derived from comparing the coefficients. From the first equation, we immediately see that a equals 1/2. Substitute a equals 1/2 into the second equation, -6 times 1/2 plus 2b equals 0. This simplifies to -3 plus 2b equals 0. Which means 2b equals 3/2. Finally, substitute a equals 1/2 and b equals 3/2 into the third equation to find c. We get -1/2 minus 3 times 3/2 plus 2c equals 0. This simplifies through -10/2 plus 2c equals 0, eventually giving us c equals 5/2. So, our particular solution is UNP equals 1/2 n squared plus 3/2 n plus 5/2. We can factor out 1/2 to make it look a bit cleaner. UNP equals 1/2 times the quantity n squared plus 3n plus 5. We have successfully determined the particular solution using undetermined coefficients, satisfying our third objective. To wrap everything up, we combine our two parts to form the general solution. Recall that our complementary solution, which handled the homogeneous part, was un super c equals a times 2 to the n plus b times 3 to the n. And our particular solution, which handled the n squared term, was un super p equals 1/2 times the quantity n squared plus 3n plus 5. Adding these together gives us the complete general solution for the 2023 Cambridge admission problem. UN equals a times 2 to the n plus b times 3 to the n plus 1/2 times the quantity n squared plus 3n plus 5. Let's recap. We identified this as a second-order non-homogeneous recurrence. Then, we solved the characteristic equation for the complementary part. We used the method of undetermined coefficients for the particular part. And finally, we combined both for the result. Notice how the exponential terms dominate for very large values of n, while the polynomial part was necessary to satisfy the specific growth of the n squared term. You've now successfully navigated a high-level university entrance problem. Great work!